And let's work one more example. In this example, we're told that an object's velocity v is given by v of t equals 2t minus 3 for values of t between 0 and 3. So for some values of v, for some values of t, I believe v is positive, and for other values it's negative. And you know what that means. We'll talk about that in just a moment. Show that the object's path ends at its starting position on the interval from 0 to 3. So as when we go from t equals 0 to t equals 3, the object is going to move around, but by the time we get to t equals 3, it's back where it started. So what I'm imagining is the following. The object starts at some point on the number line. It might go this way, and then it might go that way, but the idea is that it does end where it started. So how are we going to do this? Well, we need to look at the position function. So I hope you recall the relationship between the position function and the velocity function. The position function we typically write as s of t. If you differentiate s of t, you get the velocity function. So the derivative of the position function is the velocity function. Well, we've got this, and I think we need this. So to find s of t, we need to go backwards. In fact, we need to find an antiderivative. So let's do that. All right, so s of t is going to be the antiderivative of 2t minus 3. So that's going to be t squared minus 3t plus a constant of integration. And notice that we did not get an initial condition. We cannot solve for c. So maybe we can get by without it. So what we need to do is show that the position at time t equals 0 is equal to the position at time t equals 3. So what is s of 0? S of 0 is going to be 0 minus 0 plus c is c. Alright? So c is whatever the starting position is in this case. What about s of 3? Well, that's going to be 3 squared minus 3 times 3 plus c. Well, isn't that convenient? It's 9 minus 9 plus c, which is c. So after 3 seconds, the object does return to its starting point.